Hello friends, welcome to my lecture on stability of linear systems. Let us say 0 0 be an isolated critical point of the system, dx by dt equal to px by and dy by dt equal to qx by. First we will define a stable point. So, let us see be a path of 1, the system 1, let x equal to ft, y equal to gt be a solution of the system 1 defining parametrically the path C, and let gt dt be equal to under root ft square plus gt square be the distance between the critical point 0 0 and the point r, that is having coordinates ft gt on the path C. Then the critical point 0 0 is called stable if for every epsilon greater than 0 we can find a number delta greater than 0 such that every path C for which dt naught is less than delta, that is the distance of ft naught gt naught from origin is less than delta for some value t equal to t naught, is defined for all t greater than or equal to t naught and is such that dt is less than epsilon for t naught less than or equal to t less than delta. So, what we want that for every epsilon greater than 0 we should be able to find a number delta greater than 0 such that every path for which dt naught is less than delta for some value t equal to t naught is defined for all t greater than or equal to t naught, and dt should be less than epsilon for all t naught less than or equal to t less than epsilon. In other words, gt 0 0 will be called a stable point if every path C which is inside the circle k1 of radius delta at t equal to t naught will remain inside the circle k2 of radius epsilon for all t greater than or equal to t naught, that is every path C stays as close to 0 0 as we want it to after it gets once close enough to 0 0. So, let us see within distance delta we see. So, let us say let us look at this. Here you can see the k1 is a circle of radius delta with 0 0 center, and k2 is a circle with radius epsilon. dt you see t naught is a point, the distance of t naught the distance of this point from the curve, that is dt naught is less than delta, and then you can see that for all t greater than or equal to t naught the dt is less than epsilon. So, when this we have this this condition, that is dt is less than epsilon for all t greater than or equal to t naught less than epsilon. So, and you can see that the curve is defined for some value t equal to t naught for all the curve is defined C is defined for all t greater than or equal to t naught and dt is less than epsilon. The path every path C which is inside the circle k1 of radius delta at t equal to t naught will remain inside the circle k2 of radius epsilon. So, it remains inside the circle k2 of radius epsilon, it does not go out of the circle k2. So, this 0 0 here is a stable point. Now, let us see this asymptotically stable point is a stronger condition, the point must be stable and so satisfy one more condition. So, the critical point 0 0 will be called asymptotically stable if first of all it is stable, and then there should exist a number delta naught greater than 0 such that whenever dt naught is less than delta naught for some value t naught, then limit of ft as t goes to infinity is equal to 0 and limit of gt as t goes to infinity must be 0. That is the asymptotic stability is a stronger condition than mere stability, because in addition to stability the condition 2 requires that every path that gets sufficiently close to 0 0 ultimately approaches 0 0 as t goes to infinity. The path C of figure 1 has this property, let us see this one, the path C of figure 1 ultimately approaches to 0 0. So, this has this property, it is a stable point and it is ultimately approaching to 0 0. So, this path has this second property also. Now, a critical point is called unstable if it is not stable. For instance, the center in figure 2 here okay, the center in figure 2 and the spiral point in figure 4, this one, and the node in figure 5. Node in figure 5, they are all stable. Okay. So, here if you go to the definition of a stable point, then the condition of the stable point is satisfied. You see, we say that again, let us look at this. 0 0 is called stable if every path C which is inside the circle K1 of radius delta will remain inside the circle K2 of radius delta for all t greater than or equal to t naught, that every path C stays as close to 0 0 as we want it to after it gets once gets closed enough. So, that is satisfied in the case of figure 2, in the case of figure 2, and in the case of figure 4. Here they are going as close to 0 as we want them to be, and then figure 5. Okay. So, they are all stable points. Now, of these 3, figure 2, figure 4, figure 5, the spiral point, okay, and the node are asymptotically stable. Okay. So, let us see figure 4, the spiral point, that is figure 4, and the node in figure 5 are all are asymptotically stable. Figure 4, okay, figure 4, this is asymptotically stable. Okay. Ultimately it is approaching to 0 0, and here in figure 5 this is also ultimately approaching to 0 0. So, they are asymptotically stable. Further, if the directions of the paths in figure 4 and figure 5, okay, if the directions of the paths in figure 4 and figure 5, okay, are reversed, okay, then the spiral point and the node of these figures will become unstable. Okay. The saddle point of figure 3, this saddle point of figure 3, this is unstable. Okay. Now, let us consider critical points of a linear autonomous system. Let us consider the linear system dx by dt equal to x plus by, dy by dt equal to cx plus dy, where a, b, c and d are real constants. So, here pxy equal to ax plus by and qxy equal to cd plus cx plus dy. So, the critical points of this autonomous system are given by pxy equal to 0 and qxy equal to 0. That means ax plus by equal to 0 and cx plus dy equal to 0. Now, let us assume the condition that AD minus BC is not equal to 0, because this ax plus by equal to 0, cx plus dy equal to 0 is a homogeneous system. It is of this form. So, if the determinant of the coefficient matrix is not equal to 0, then x y will be 0 0. Okay. Determinant of the coefficient matrix, this is not equal to 0, then we know that the only solution that is possible is the trivial solution. So, x equal to 0 and y equal to 0, and therefore 0 0 will be the only solution of pxy equal to 0 and qxy equal to 0, if we assume the condition AD minus BC not equal to 0. So, 0 0 is the only critical point of this system 2. Now, let us solve the system 2. When we solve this system of homogeneous system of linear equations, linear system, then we have x equal to a e to lambda t and y equal to b lambda t. Solutions of this form we get. And so, if x equal to a e raised to the power lambda t and y equal to b raised to the power lambda t are solutions of 2, then we have a lambda e to the power lambda t equal to a e to the power lambda t dx by dt, x is equal to a e raised to the power lambda t. So, dx by dt will be equal to a lambda e raised to the power lambda t, and y equal to b e raised to the power lambda t will give dy by dt equal to b lambda e raised to the power lambda t. So, putting the values of dx by dt, dy by dt, we have this equation, a lambda e raised to power lambda t equal to a into a e raised to power lambda t plus b into b e raised to power lambda t, and b lambda e to the power lambda t equal to C A e to the power lambda t plus d v e raised to the power lambda t. Now, e to the power lambda t is never 0, so we can cancel e to the power lambda t from this equation and this equation, and we can write a times lambda minus a minus b v equal to 0, b times lambda minus d minus C A equal to 0. Now, from this, okay, we can write it as lambda minus a minus b and lambda minus d a, oh, lambda minus c a b. Okay. Now, if the determinant of this coefficient matrix lambda minus a minus b lambda minus d minus c is not equal to 0, then what will happen? We will have a b equal to 0 0. Okay. So, when a is equal to 0 and b equal to 0, we will get the trivial solution, okay, of the autonomous system. So, in order to have a non-trivial solution, let us assume that determinant of lambda minus a minus b lambda minus d minus c, this equal to 0, okay, and this will give us a second order equation, polynomial equation in lambda of degree 2. So, lambda square minus a plus d into lambda plus a d minus b c equal to 0. Now, this equation is called as a characteristic equation of lambda. Since we have assumed that a d minus b c is not equal to 0, lambda equal to 0 can never be a root of this equation. Okay. Now, let us say lambda 1 and lambda 2 be the two roots of this characteristic equation. We have a characteristic equation in a polynomial equation in lambda of degree 2. So, it will have two roots. So, let us say lambda 1 and lambda 2 be the two roots of the characteristic equation. Then we shall see that the nature of the critical point, whether it is a center or it is a node, okay, that nature, and it is a stable or asymptotically stable or it is unstable, it will depend upon the nature of the roots lambda 1 and lambda 2. So, in this regard, now here we have 5 cases, or as such we have 3 cases when we have two roots of the second order equation. They may be real and distinct, that is one case. Then they may be complex conjugate of each other, and the third case is that they are real and they are equal, okay. But here we have 5 cases. So, lambda 1 and lambda 2 are real, unequal and of the same sign. So, we have 2 cases, sub cases of the situation where lambda 1 and lambda 2 are real and unequal. One is that of they are real and unequal and of the same sign, and the other one is that they are real, unequal and are of opposite sign. And then in the conjugate complex, again we have 2 cases, that is lambda 1 and lambda 2 are conjugate complex of each other, and they are not purely imaginary, that is their real part is not equal to 0. And then the one more case, that their real part is 0. So, lambda 1 and lambda 2 are purely imaginary, and the fifth case is lambda 1 and lambda 2 are real and equal. Okay. So, let us see now, first we discuss the case when the characteristic equation has 2 roots lambda 1 and lambda 2, they are real, unequal and are of the same sign. Okay. Then the critical point 0 0 of the linear system 2 is a node. Okay. So, let us see, we have let us say lambda 1 and lambda 2 be 2 roots of the characteristic equation, and they may be both negative. Okay. So, they are of the same sign. So, let us take them to both to be negative, and suppose lambda 1 and lambda 2 satisfy this inequality, lambda 1 is less than lambda 2. The general solution of the system 2 may be written as, now let us see how we write this system solution. See, we have seen that this equation has 2 roots lambda 1 and lambda 2, and we are assuming that they are real, unequal and of the same sign. Then what happens here, that for the value of lambda 1 and lambda 2, okay, these two equations give us for lambda 1 we get the values of a and b as say a1 and b1. Okay. For the value lambda 2 we get the values a2 and b2. Okay. Then what will happen, corresponding to lambda 1, x will be equal to a1 e raised to the power lambda 1 t, y will be equal to b1 e raised to the power lambda 1 t. So, this is one solution, and corresponding to the other root lambda 2, we will have x equal to a2 e raised to the power lambda 2t and y equal to b2 e raised to the power lambda 2t. Okay. So, corresponding to one value lambda 1, we have a solution of this equation. Okay. We take the values of a and b corresponding to lambda 1 as a1 b1, or corresponding to lambda 2 we take the other values of a and b, they are a2 and b2. So, then x by equal to a1 e to power lambda 1 t by equal to b1 e to the power lambda 1 t, this is one set of solution and this is another set of solution. They are linearly independent of each other, and in the case of homogeneous system, linear homogeneous system, we write the general solution as the linear combination of x equal to C1 A1 plus C2 B1 x equal to C1 A1 e raised to power lambda 1 t plus C2 A2 e raised to power lambda 2 t, because corresponding to lambda 1 the solution is A1 e raised to power lambda 1 t, and corresponding to lambda 2 the solution is A2 e raised to power lambda 2 t. So, general solution will be given by x equal to C1 A1 e raised to power lambda 1 t, C2 A2 e raised to power lambda 2 t, and y will be C1 B1 e raised to power lambda 1 t by plus C2 E2 B2 e raised to power lambda 2 t. Now, A1 B1 A2 B2 are definite constants, they are given by this equation. Okay, they are given by this equation. So, they are definite constant, and moreover that these are linearly linearly independent solutions. Okay. X by equal to x equal to a1 e raised to power lambda 1 t by equal to b1 e raised to power lambda 1 t, this set of solution is linearly independent to the other one, x by equal to x equal to a2 e raised to power lambda 2 t by equal to b2 e raised to power lambda 2 t. So, what we get is a1 b2 is not equal to a2 b1. So, that condition comes from there, and C1 and C2 are two arbitrary constants. Now, let us choose C2 equal to 0. Okay. Let us choose C2 equal to 0 here, then x is equal to C1 a1 e raised to power lambda 1 t by equal to C1 b1 e raised to the power lambda 1 t. So, we get this when we choose C2 equal to 0, the general solution gives us this. Now, here you can see C1 when C1 is less than 0, okay, when C1 is greater than 0, these solutions, okay, these solution 6, okay, represent a path consisting of half of the line b1 x equal to a1 by. If you eliminate C1 here, what you get? These two give you b1 x equal to a1 by, okay, when we eliminate this. Now, a1 and b1 are definite constants. So, let us take, say, suppose a1 and b1 are both having the same sign, either positive or negative, then what will happen? Then we will have choosing C2 equal to 0, we get x equal to C1 a1 e raised to power lambda 1 t by equal to C1 b1 e raised to power lambda 1 t. When you eliminate C1 here, you get b1 x equal to a1 by. Now, let us take the first, we take the case when C1 is positive, then what will happen? E raised to power lambda 1 t is always positive. So, a1 e raised to C1 e raised to power lambda 1 t will be positive, and C1 here what will happen is that, let us take a1 and b1 both to be positive. Then what will happen? You see here, if I take a1 b1 this line b1 x equal to a1 by this line, here what they are doing is that suppose a1 b1 have different signs, then what will happen is that if a1 b1 have different signs, suppose a1 is negative and b1 is positive, then we will have in the in this quadrant, okay, this line, this half line we will have, okay, because we are taking C1 to be greater than 0, okay, a1 x equal to C1 a1 e raised to power lambda 1 t, C1 we are taking positive. So, if I take a1 to be negative and b1 to be positive, okay, then what will happen is that we will have this half line, okay. The other half line we will get here, which comes from when you take C1 to be negative. So, for any C1 greater than 0, these represent a path consisting of half of the line b1x equal to a1 by, and slope of the line will be b1 upon a1. b1 upon slope of the line will be, you see here, by equal to b1 upon a1 into x. So, these when c1 is greater than 0, these solutions represent a path consisting of half of the line b1x equal to a1 by with slope b1 by a1. And when you take c1 to be less than 0, we have chosen a1 to be negative, b1 to be positive. If I take c1 to be less than 0, then what will happen? X and y, x will be positive, y will be negative. So, we will get the other half line, okay, this half line we will get. And so, when c1 is less than 0, these solutions represent the other half of this line. Since lambda 1 is negative, both of these half lines paths approach 0 0 as t goes to infinity. You see, lambda 1 is less than 0. So, when t goes to plus infinity, x goes to 0 and y goes to 0. Okay. So, since lambda 1 is less than 0, both of these half line paths approach 0 0 as t goes to infinity. Also, we notice that y over x is equal to b1 by x, b1 by a1. So, these two paths enter 0 0 with slope b1 by a1, you can see here. Okay. These two half line paths enter 0 0 with slope b1 over a1. Now, let us choose c1 equal to 0. When we take c1 equal to 0 in the general solution, we get x equal to c2 a2 e to power lambda 2 t, y equal to c2 b2 e raised to the power lambda 2 t. So, similarly for any c2 greater than 0, now again we choose c2 greater than 0. Okay. The solutions, these solutions 7 represent a path consisting of half of line b2x equal to a2y. So, here again when you eliminate c2, what we will get is b2x equal to a2y. So, when c2 is less than 0, okay, when c2 is less than 0, the paths so represented consist of the c2 greater than 0 will give us half of the path, you can see here, this half of the path, okay, b2x equal to a2y, this half path and this is another half path. So, these two half line paths also approach 0 0. Now, let us see again lambda 2 is negative, because we have chosen lambda 1 and lambda 2 to be of the same sign, and that is negative. So, when t goes to plus infinity, x and y go to 0, and therefore, these two half line paths also approach 0 0 as t goes to infinity, and these two half line paths enter with slope b2 by a2. You can see in this, these two half line paths, okay, enter 0 0 with the slope given by y equal to b2 by a2. Y equal to the question is y equal to b2 by a2 into x. So, they enter the 0 0 with the slope b2 by a2. Now, thus the solutions 6 and 7, okay, provide us with 4 half line paths. You see, 2 half line paths we get from here and 2 half line paths we get from here. Okay. So, we get 2 half line paths, 4 half line paths which all approach and enter 0 0 as t goes to infinity. We can see here, this is one half line path, this is another half line path, this is third half line path, this is fourth half line path. They all approach 0 0, and these half line paths approach 0 0 with slope b2 by a2, while these two half line paths approach 0 0 with slope b1 by a1. Thus, we have 4 half line paths which all approach and enter 0 0 with as t goes to infinity. Now, let us assume that c1 is not equal to 0 and c2 is not equal to 0. Then the general solution represents non-rectilinear paths. Let us see, we have y equal to c1 b1 e to the power lambda 1 t, c2 b2 e to the power lambda 2 t, x is c1 a1 e to the power lambda t plus c2 a2 e to the power lambda 2 t. Now, lambda 1 is less than lambda 2 less than 0, we have assumed that. So, what will happen is that now this equation we can write as c1 b1 over c2, because c2 is not 0, we can divide by c2, and e to the power lambda 2 t also we can divide in the numerator and denominator. So, c1 b1 over c2 e to the power lambda 1 minus lambda 2 into t plus b2 c1 a1 over c2 e to the power lambda 1 minus lambda 2 t into t plus a2. Now, lambda 1 is less than lambda 2, so lambda 1 minus lambda 2 is negative as t goes to plus infinity. e to the power lambda 1 minus lambda 2 t goes to 0, and so this part goes to 0, this part goes to 0, and therefore limit of by over x as t goes to infinity is equal to b2 by a2. So, all these paths, non-rectilinear paths, they enter 0 0 with limiting slope, okay, limiting slope b2 by a2. So, we can see that in the figure here. See, they are non-rectilinear paths, they are all non-rectilinear paths. This one, this one, this one, this one, they are all non-rectilinear paths, these ones, okay. They all enter 0 0, okay, with limiting slope b2 by a2. You can see this path enters, okay, with slope b2 by a2. At the origin, this line b2x equal to a2 by is tangent to all these paths, and this line is having slope b2 by a2. So, all these non-rectilinear paths enter 0 0 with limiting slope b2 by a2, and thus we have the same. Now let us see. Let us assume that lambda 1 is greater than lambda 2 greater than 0. So, we now assume that lambda 1 and lambda 2 are both positive. Then the general solution is still of the same form, x equal to c1 a1 e to power lambda 1 t, c2 a2 e to power lambda 2 t, c1 b1 by equal to c1 b1 e to power lambda 1 t, c2 b2 e to power lambda 2 t. Now, we choose c2 equal to 0. So, x equal to c1 a1 e to power lambda 1 t by equal to c1 b1 e to power lambda 1 t, and x is equal to if we choose c1 0, c1 ko if we choose c1 equal to 0, then x becomes c2 a2 e to power lambda 2 t by is equal to c2 b2 e to power lambda t. So, we get the solutions of the same form as in the case of lambda 1 and lambda 2 both being negative. Now, what is the difference here? We have the same situation as before, except that all the paths approach and enter 0 0 as t goes to minus infinity, because lambda 1 and lambda 2 are positive. So, they enter 0 0 when t goes to minus infinity. The qualitative diagram remains unchanged, except that all the arrows now point in the opposite direction, okay. So, hence the critical point 0 0 is still a node, but it is unstable in this case. So, see, we had this situation earlier, okay. Now, the directions will be opposite to these directions, okay, and therefore, we will still have a node, but it will be unstable node. So, with that we come to the end of this lecture. Thank you very much for your attention.